Last few lectures we have studied about the Boolean function minimization, in which we have studied three different techniques how to minimize a Boolean expression. First is the minimization using the Boolean algebra. We have different types of postulates, different laws, different properties. By using these properties, we can reduce the Boolean expression. Another one was the Karnaugh map. With the help of Karnaugh map, we can minimize SOP or POS, which are represented in the standard form, and that can be minimized to the minimal SOP or POS form. And in the last lecture yesterday, we have studied about the tabulation method. That was the Quinn-Mikulski method, which is an algorithm-based method and which is used when the number of input variables are more than 5. So we have to use these all our knowledge in the next coming some lectures when we are going to design a digital circuit, and the very first digital circuit which we are going to design or which we are going to discuss are the combinational logic circuits. So let's first discuss what the combination logic circuits are and how they looks like. The combination logic circuits consist of logic gates with outputs that are determined entirely by the present value of the input. That means in combinational circuits, we have no memory element. So when we give input at the present time, at the same time you will get some output. The combination circuit might be two-level logic, that is SOP or POS, or multi-level. We'll discuss later what the level means. So this is the block diagram of a combinational circuit that we have here. These are the inputs, that n number of inputs it may have, and it may have m number of outputs. So there is no boundation, as in case of the logic gate. When we have studied two input logic gate, we have studied AND gate, OR gate, NOT gate, XOR gate, NAND, NOR, and XNOR gate. And in all gates, we have only single output, and the input may be either 2 input, 3 input, 4 input. So when the case comes of the logic combinational circuit, then the combinational circuit may have n number of inputs and m number of outputs. And these inputs and outputs are defined by the characteristics or the specifications of the circuit which we are going to be designing. The two important procedure for the combinational circuits are, first one is the analysis. In the analysis portion, we are given the circuit schematic, and we have to explain its behavior. That means we have to draw the truth table. Given a circuit, we have to draw the truth table. On the designing part, we are given the specifications, and from the specifications we have to construct a truth table. Then we have to minimize that truth table with the help of K-map or tabulation method or Boolean algebra. Then we have to design the circuit. So there are the two processes for the combinational circuits. First one is analysis, and the second one is design. Sorry. Now let's start with the first analysis process. How the analysis is done. The process is like, label all logic gate outputs and primary inputs. We gave any arbitrary name X, Y, Z, A, B, C, D, T1, T2, T3, all inputs and all the outputs of the gates. Primary inputs are the basic input which are given externally. So here we'll discuss in detail what the primary inputs and the outputs are. Next, starting from the primary inputs, represent outputs in terms of their input variables. We will have gates. So either we have AND operation, we will have OR operation, or we have NOT operation. So these are the basic operations, and we have to label all the operations. In the step 3, repeat step 2 until we reach the output, means for each and every input and output of the gate, we have to nominate it with the arbitrary variable. We have to define with the variable, and we have to find out the value of the variable with the help of our knowledge we have studied so far. Then represent primary output in terms of the primary input, means internal value what you have assigned that must be eliminated, and the main output will be represented in terms of the primary input A, B, C, D or X, Y, Z, whatever it is. Suppose this is the circuit. We have the first AND gate and the input is A, B, C. Another one is OR gate. It is A, B, C again. AND gate input are A, B. AND gate input is AC. AND gate input is BC. So this A, B, C, these are called the primary inputs, which are at the level 1. So this gate level which has input only as the primary input is known as level 1. So this is level 2. The output of the primary level 1 is fed to the next level, that is known as level 2. So this gate and this gate will be level 2. This is level 3 because the output of level 2 is the input to NOT gate. This is known as level 3, and the output of the level 3 is given to the next gate. This is level 4. So the level 1, level 2, level 3, level 4 and level 5, because the output of the level 4 is input to the next level, that is the known as a level 5. So these are the levels 1, 2, 3, 4, 5. So here in this term we define the level. What we have level all the logic gate output and primary input. So these are the logic levels. So what we have done, we are given a primary input ABC. Then the output of the gates we have nominated as it is T2. Output we have defined T1. Here is the output F2. So this output of the NOT gate will be F2 dash. This is your T3, and we have output F1. So what we have to do, we have to find out the value of F1 and F2. These are the final output of the combinational circuit in terms of the primary input ABC. So this is the analysis process. So here F2 we can define A and B from this gate, then A and C from this gate, B and C from this gate, and these all outputs are odd. So we can say that F2 is AB or AC or BC. So this is your F2, which is defined in terms of the primary input ABC. Similarly, we get T1 is nothing but A plus B plus C. T1 is A plus B plus C because this is the OR gate. T2 is nothing but A, B, C AND gate. T2 is AND gate ABC. T3 is nothing but F2 dash and T1. Sorry. So this is your F2. We have to find out its complement and multiply or end with the T1. So we'll get the value of T3. And F1 is nothing but T2 or T1. So F1 is T2 or T1. So here in this expression, in expression of T3, we have to put the value of T1, then solve it with the help of Boolean algebra. Now put the value of T2 and T3 in F1, we can simplify the value of the F1 in terms of A, B, C. So this is the analysis process. How we can analyze the input output characteristics of a given combination logic circuit. So after getting the value of F1 and F2 in terms of ABC, we can draw the truth table, and the value of the truth table will be ABC is the input. Then we have to find out T1, we have to find out T2, we have to find out T3, and the relation is T1 is A plus B plus C, ABC, F2 T1, F2 dash T1. So we have to put these numerical values of this binary value. Then we can find out the value of F1 and F2. Now let us take a quick view of the analysis design process. So in the design, we are given the specifications, then what we have to design. From the specification, determine the required number of inputs and outputs. First of all, you have to find out that how many number of inputs are required and how many number of outputs are required for a given specification. Then assign a binary variable to each input and output. Suppose we have defined ABC to the input and XYZ to the output like this. It may be arbitrary. You may take any variable to define input and output. Then derive the truth table and derive a truth table that defines the required relationship between input and output, and that relation will be given in the specification of the question. That will always be given in the specification of the question. Then perform logic minimization, and you can perform logic minimization if the variables are of up to 4 input variables. Then it is preferred that you use K-map. After the logic minimization with the help of the K-map, you will get the Boolean expression. Then simply draw the circuit with the help of AND or AND NOT gate from the for the Boolean expression which is obtained with the help of K-map. Now let us take an example that how the specifications are given. Suppose we have to design a circuit that takes input as BCD and converts this input into the XS3 code. So this process or this example is known to be as BCD to XS3 code converter. So the input is BCD and output is XS3. So in the first step, we have to find out that how many numbers are required to represent a BCD and XS3, and the answer is 4. We have to we require 4 bits to represent a BCD and 4 bit to express XS3. So first of all, we have to write all 3 BCD all 10 BCD combinations which are possible with 4 input variables. Suppose this is the BCD. So we have A, B, C, D as input, and the value of BCD is from 0 to 9. 10, 11, 12, 13, 14, 15. The rest of the states are unused, and we consider it as don't care condition. We have discussed in the last lecture that what the don't care means. So here the rest of the state will be considered as don't care. Next we write the corresponding XS3 code. XS3 is nothing but it is 3 access to BCD. So we have BCD plus 3 is XS3. So for an example, if the BCD is 0, 0, 0, 0, that is 0, then the XS3 will be 3. 3 is represented as 0, 0, 1, 1. So we have discussed already that what the XS3 code, how to get XS3 code. Randomly, you can take like if BCD is 3, then the XS3 will be 6. So 3 is represented as 0, 0, 1, 1. While 3 in XS3 is 6, 0, 1, 1, 0. So with the step 2nd and 3, what we have done, we have find out the number of input variable. As per the specification, we have constructed a truth table. Now we have to minimize this truth table with the help of K-map. So this is the K-map I have drawn here for the value of Z. Let us take a quick look on the value of Z. Z is 1 for, it may be easy if you write down this table and the K-map in your copy. So value of Z is 1 for 0, 2, 4, 6 and 8. So we have to plot it in the K-map. 0, 2, 4, 6, 8. Here's the K-map. 0, 2, 4, 6, 8. These are the 5 1 value SO of the SOP. And we have 10, 11, 12, 13, 14, 15. These are the don't care conditions. So when we make a pair, we have this 4 and this 4, which combinedly make an octet. And when we move across the octet, when we move across this column, value of AB is changing. When I'm moving from this column to this column, the value of C is changing, but the D is constant, and the value of D is 0. That means Z equals to D bar, like this. And similarly, we have to draw the K-map for Y. Again, Y has, we can look here in this table, Y has the value 1 at 0, 3, 4, 7, 8. So y has value 0, 3, 4, 7, 8. So again we have to draw the K map in this as 0, 3, 4, 6, 0, 3, 4, 7, 8, and the rest of the conditions are don't care. Then again we have this quad and this quad. So for this quad, value of CD is constant, that is CD. AB is changing. For this quad, value of the CD is 1 1, that is CD, and for this it is C bar D bar. So the value of Y is CD plus C bar D bar. In the same manner, we can find out the value of X and we can find out the value of W. You can write down or you can note down the same. So what we have done in the first step, we have to find out the number of inputs and outputs. We have to construct a truth table, and after the truth table is constructed as per the specification, we have to solve the output for the with the help of K-map to find out the minimum number of minimal SOP or POS terms, and from here we get Z equals to D bar, Y equals to CD plus C bar D bar. You may directly implement it. X equals to B bar C plus B bar D plus B C bar D bar, and W equals to A plus BC plus BD. So, and the last step is to draw the circuit, and here I have tried to draw the circuit, the logic diagram of a BCD to XS3 code converter. So, what expression we have found out in the previous slide that has been implemented, and this is known as a combinational circuit which has 4 inputs as BCD, and the output will be of 4 bits, that is of XS3. So whenever we give it a valid BCD, the output will be a valid XS3 combination. So this is how any code converter can be designed. So you at home may try to design a code converter that converts 3-bit gray code to a binary number. So that question has been asked 3 or 4 times in your end-term university examination. You all have to try at home that convert a 3-input combinational circuit which takes 3-input binary gray code and converts it into the binary number. So this will be a home exercise for you. If you find any difficulty, then you may contact. Then I may try to sort out your problems. Suppose now move to the next topic, that is the binary adder. Now we are moving towards the combinational circuit, which are they are arithmetic circuits. Sorry. Now from the binary adders, we'll move to the BCD adders and other type of adders which are used in your computer, and how the addition is takes place in your system. There we are going to define here how the all arithmetic operations takes place in your computer. That's we are going to design in the combination circuit. Now adder is an important component in many logic circuits. We have first is the half adder. So when we talk about the adder, then for an adder there are 2 bits X and Y. It will produce 2-bit output. One is sum represented by S, and one will be the carry. So when you add 2 numbers, there will be a sum and there will be a carry. For the half adder, we define half adder is adder which adds 2 bits X and Y and produces an output CS, where C is the carry, sum is S is the sum. So it should be the block diagram of the half adder. It should have 2 inputs X and Y, half HA is half adder, and 2 outputs sum and carry. That is the block diagram. Now we'll try to design how half adder is designed. So input is X and Y, output is sum and carry. So with the 2 inputs, we have 4 possible combinations. So I have written 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 possible combinations for the input. And the operation will be X plus Y. So we add 0 plus 0. When we add 0 plus 0, sum is 0, carry is 0. 0 plus 1, Sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. And 1 plus 1, 1 plus 1 is 2, so then sum is 0, carry is 1. So this is the truth table. How the truth table is constructed with the help of the uh, input specifications, that half adder is equal, output equals to x plus y. So we have to solve the expression for the output. So the expression for the sum is s equals to x bar y plus x y bar. So this is your x bar y